Alrighty, howdy folks. I just want to cover chapter 8 today, both sections 1 and 2. I have a feeling that I can get done with it relatively quickly. And this is about arc length. I don't want to make a big fuss about this one. These two sections, there's one formula for each section that I want you to know and be able to use it, and that's it. Okay. All right, what's this about? Well, let's say we have a curve y equals f of x, and on the interval a to b, let's say we want to find the length of that arc, length of that curve. All right. One thing you can do is if you just take a itty bitty piece of this one, okay, that itty bitty piece, even if it is curved, because it is so small, we could approximate that to be a straight line. And that is what we are talking about as the differential length dl that I have shown here. Okay, and in that case, dx is the x length of that piece and dy is the y length of that piece. And because that's a right triangle that you see, we can apply the Pythagoras theorem and say dl square is equal to dx square plus dy square. Okay, and so the differential arc length dl is just simply the square root of dx square plus dy square. Cool. Now uh, we can we can factor out a dx out of this, and uh, if we do that, we end up getting this one. Okay, so if dl is equal to all of this, L itself would be an integral of that from A to B. Okay, if you don't understand the derivation of this formula, don't worry too much about it. All I want is that you remember this formula. L equals integral A to B of square root of 1 plus dy dx square, that quantity, okay? Dx with respect to x. Okay, let me apply that to a particular problem. And so find the exact length of the curve, and you're given some y equals, y means f of x equals, and the interval is 1 to 2, right? So clearly, to find the arc length, we'll use this formula, and we recognize that in this case, a must be 1 because we have interval 1 less than or equal to x less than or equal to 2 means x lies between 1 and 2. So a is 1 and b is 2, right? Okay, what else do we need? Oh, we need dy dx. Are we in a position to finding dy dx? Yeah, we got y to be this x cube over 3 plus 1 over 4x. So f prime of x should be just the derivative of that, which turns out to be this. Right. So my strategy is typically to figure out the 1 plus dy dx, 1 plus the square of dy dx separately, okay, or 1 plus f prime of x square separately, and then put it in the integral. So when I do that, 1 plus this quantity square, and if you expand this out using a minus b, the quantity square is a square minus 2ab plus b square, you end up getting this. Okay, x square, the quantity square is x to the 4 minus 2x square times 1 over 4x square simplified turns out to be 1/2, and plus 1 over 16x to the 4. But notice 1 minus 1/2 is just 1/2 plus 1/2, right? So this reduces to that. Now there's something interesting here. Would you agree this stuff inside the square brackets was the square of x square minus 1 over 4x square? So what do you think x to the 4 plus 1/2 plus 1 over 16x to the 4 would be? It's just that you change this to x square plus 1 over 4x square. So that whole thing simplifies to x square plus 1 over 4x square, the quantity square. And when we take the square root of it, let's just take the positive value of it, x square plus 1 over 4x square. Cool. And so that means arc length is just integral 1 to 2 of that, and you plug and chug, integrate. That integral is x cubed over 3 minus 1 over 4x, and integrated from 1 to 2, plug numbers, and you got the length of the arc. Would you be able to do something like this? That's all. A straightforward formula. You're given y, you're given a and b, take the derivative, square, blah blah, all that stuff, you're done. And finding the surface area is the next part. Area of a surface of revolution. What's the idea here? The idea is, if you have a curve y equals f of x, just like the previous one, on the interval a to b, and you take that curve and you rotate it about, say, the x-axis. Earlier in chapter 6, we learned about how to find the volume of something like that. But here, we are not interested in the volume. Instead, we are interested in the surface area of that resulting thing. Okay? So, the area of the resulting surface, that is simply given by 2 pi times y times square root of 1 plus dy dx square. So the arc length was just square root of 1 plus dy dx square, right? Dx. Here you just need to multiply that by y, and of course also by 2 pi, and integrate. And we can, instead of dy dx, we can write f prime of x. Okay. So a problem, when it comes to solving a problem, find the exact area of the surface. Let's say we are given y equals square root of 1 plus e to the x. As before, recognize what a is. You know the formula that you're going to plug all of this into. So a is, what do you say? 0, yep. B, 1, yep. And we just need to find dy dx, and then square it and add 1 and take the square root. So f of x, okay, square root of this turns out to be this. If you feel that I'm going over somewhat fast, it's because I think this is very, very straightforward. That's the only reason. All right, okay, now let's square that and add. What is this going to be? Well, the top is going to be e to the 2x when we square this, and the bottom is going to be 4 times 1 plus e to the x. And when we add that to 1, on the top we'll have 4 times 1 plus e to the x plus e to the 2x. And the top is, again, when we split this back, we get x to the 4 plus 1 half plus 1 over 16 x to the 4. No, we don't. I'm an idiot. Crud. Okay, let me make some changes. I think I copied it wrong. Pause. Alrighty, I'm back. I fixed it. I apologize, folks. I'm sorry. I hate making mistakes like that. Okay. Oh, where were we? It ends up. All right. So we got. Ooh, that's where I. Yep. This is where I had stated something that was wrong. Okay, so I fixed it. If you look at the top, that's a e to the 2x, excuse me, plus 4e to the x plus 4, right? That's nothing but e to the x plus 2, the quantity square. Okay, if you don't believe me, just expand this out, FOIL this out. Would you get e to the 2x plus 2 times e to the x is 4e to the x plus 4? Yep. So that's just e to the x plus 2 square over this one. Now, if we take the square root of the top because it's squared, and let's say we pick the positive root, and we have this. So, surface area being given by this, recognize that y in this case is square root of 1 plus e to the x, right? So if we plug that, then we notice the square root of 1 plus e to the x, and in the denominator the square root of 1 plus e to the x, they cancel and the integral becomes a simple one. Okay, and the integral of e to the 1/2, I yank that outside of the integral, and integral e to the x is e to the x. Integral of 2 with respect to x is 2x, and we need to use the limits of integration 1 to 2, right? And when we do plug, chug, and simplify, this is the answer. Isn't that really simple? That's all I expect you to understand in these two sections. So it took barely some 10 minutes for me to explain this whole thing. Cool. All right. That's it, folks.